presentation. So I'm going to just dive in, I think, in the worlds of PDE. So you've heard these days many things about differential equations and how to solve them. So my question to how to start is, OK, how do we solve a PDE? So when we have a PDE, a partial differential equation, we have normally three objects, like a differential operator L that might depend on a parameter lambda, so a parametric PDE. Then we have a right-hand side function f and a boundary condition. So we are assuming that we are in a domain. And lambda, f, and u are in some spaces. Normally, we can assume that there are some function spaces. The precise nature of these spaces now is not important. And what are we interested to do? We can think at the basic case 0, where we have one lambda fixed, one right-hand side function f fixed. Then this is not even, this is a just simple PDE. And we have many methods to solve them, like numerical methods. I'm sure you've heard many of them. We've also spoken about them in the last days. But we can think of this problem on a level of abstraction above and think of at an operator that maps lambda and f to the solution of the PDE. So now this is a map that takes two objects or functions in lambda and f and outputs the solution of this PDE. Okay? And this is, of course, a bit of a more complex object because it's a map between potentially infinite dimensional spaces. So now I look at, first I said, OK, the case 0 would be when they're fixed. Now let's think that lambda is fixed in that operator and f varies. So this is now a sub-object of that h operator, and it's an operator that maps my right-hand side function f to u. So if I would have this operator, you could give me a right-hand side function, and it could give you the solution of the PDE with that right-hand side function, OK? And in theory of partial differential equations, there are many methods for solving PDEs, and one of these, a very powerful tool to solve PDEs, is under the name of Green, the Green's function. I'm sure you heard of it. What is it? Is that if this operator L is linear, then there might exist a function, here denoted as g, that that enables me to express the solution as an integral of this Green function. So the Green function is defined as the impulse response of the operator. So it's the Green, when I input the Green function, it gives me an impulse, a delta function response. And then this means that for the, I think it's called the superposition principle, I can construct a solution by integrating over the domain against my right-hand side function. OK, so what I can assume then is that, OK, this operator g, I express it through the Green function as the integral over the Green function that might exist against f. And note that this operator g is now the inverse of my differential operator, right? Because my differential operator takes u and gives me back f, and g takes f, the right-hand side function, and gives me back u. OK, this is now just a visualization because I think there are different objects coming in here, and some are 2-dimensional, some are 1-dimensional. So maybe let's look at an example. If we see, so here I took a PDE with this differential operator, so it's just a second derivative with some perturbation in lambda. And if you fix a column, you can see for a fixed value of lambda. So for a lambda, you have a Green function. So I actually chose a PDE where I can actually analytically compute the Green function, which is written here. So for every column, I have the Green function as a 2-dimensional function, right? It's in x and y. And then what you do when you compute the solution is you integrate out the y against f. So here, two different right-hand side functions enter on the left, and these are the corresponding solutions for those right-hand side functions against the Green function. And this is the same for another value of lambda and another value of lambda. OK. Good. Then we have this operator now that we are interested in learn. And we want to do it in a data-driven method. So we want to learn it by observing some data points. And these data points are in general functions. So assume that we observe f and u, and we have many of them. And what we want to do is we want to recover this operator g. But what I just said here is that this then becomes equivalent on learning a function, a bivariate function g from R2 to R, which is our green function. With maybe a little caveat is that the observations that I have on the green function are not direct observations of g, but are observations of their integral against f. We're going to explain this in a moment. Okay, and how do we want to learn this operator, or the green function, in a probabilistic framework? I think I don't need to explain anymore why it's important to do that in a probabilistic framework, but yeah, more will follow about the motivation. And we do this through Gaussian process regression, and I think Tony gave a very good introduction also today about Gaussian processes, so I think I need to repeat that. But so we do a special case, though, of GP regression, because our observations are not direct observations of a solution, but they are observations against a linear operator. In which sense? So if we define the linear operator A, f, so for every f, we have the operator that acts on G in this way, which is, these are my observations ui, sorry, that are the integrals of G over f. So I put a prior on G, I choose a kernel and a mean function, and then a likelihood, and I can compute the posterior and the covariance through analytically through these formulas, where these objects, of course, are then discretized. So here there are two objects coming in that I'm kind of hiding behind the carpet, which are that when I say that I observe functions, I actually observe them on a grid, and these are the grids that I use to computing these integrals. But in general, I can compute this mean and covariance and get my posterior on the green function, and automatically then on the operator. I hope I'm getting you there. So here an experiment to show this. So let's take again the PDE of before with this differential operator, and let's have n observations, or a number of observations of right-hand side function and correspondent solutions. Then we choose a kernel. In this case, I chose a Matern kernel that I can divide into a product kernel, because this makes the integrals to compute easier. And here what you can see is the, so maybe I should explain a bit this plot. So here we want to, through this observation, to approximate the green function. Here on the right, you can see the true solution. And moving on the left, you have the approximation, or the mean, after 3 observations, and here after 8 observations. And what you can see here, since this is a distribution over the green function, this comes also with some variance. And to visualize it, I just draw samples from it. Since visualizing the uncertainty in 2 dimensions is a bit more tricky, what you can claim is that if the samples differ from each other, then you have a higher variance, and if they don't, like they're pretty similar to each other, then you have a lower variance. And this is the case here when the solution looks quite approximate, or very not that good approximation. You see that the samples differ a lot, where they become always more close to each other or similar when you have a good approximation. Okay, this is just actually a nice, I just wanted to produce some nice samples. So what I want to say is that in a Bayesian setting, of course, you can encode information that you have about your function in the prior, because this is a nice thing about putting a prior, is that if you know something, you can encode it in the kernel. And this is just an example where we encode in the kernel that the samples should be symmetric, because this is something that we know about the green function, is that it's symmetric along the axis, and then you can actually encode this in the kernel, and then produce some nice samples that are symmetric along the x-axis. Okay, so this was the case, as I said, as we fixed a lambda, and we have the operator that maps f to u, which is a linear operator and an integral operator over the green function. Now, what happens if I now look back at how I started? So I want what I actually started with was an operator that varied also in the parameter lambda. And this might be a bit more of a complex thing to do, because this function may also be nonlinear in lambda. So this GP framework doesn't work very well, or doesn't work actually. So what is the next step? And this might seem a bit of a jump, but what I could do is that I could use a neural network or a deep neural network to find the solution to this operator. And I will explain this in a moment, but these are new methods that have been recently very popular or powerful too. Like you may heard of this. They are known under neural operators or Fourier neural operators, depot nets. These are methods that actually do exactly this. They want to approximate an operator that maps to the solution of a PDE. And how do they do that? Well, they iteratively approximate. So the neural network is seen in this iteration that now we're going to look a bit more closely. So what we do is we iteratively approximate the solution. How? So at every iteration, we integrate the output of the previous layer against the green function. And now I'm calling it the green function, but this is actually a neural network. But what we did, you think at it if you want to do that GP with a neural network, basically it's what you're doing, right? You're learning some features. Plus, you can combine the integral with a linear component and an activation function. So this is, so you're at every iteration, you're entering in the previous layer here and here, plus you have an inner neural network, which is what I call the green function. Why? Because the case of before gives you an intuition of that, why there is this construction. Because if you have this these parameters w equal to 0 and one layer, then you actually end up exactly with the thing of before, where this part is not there, and you have actually a solution that is motivated by the theory of PDEs known as green function. And well, in these deep neural networks, like, uncertainty becomes even more important. So in general, PDEs that describe dynamical systems can have very subtle or complicated behavior that are very difficult to spot by human eyes. And so these models are thought to also solve very complex dynamical systems and PDEs, and they are high in nonlinear. So even in this case, we wanted to enforce these methods with uncertainty quantifications. And how do we do that? Well, actually, Philip already talked about this on Monday if you were at the talk, but I can recap how we can do it. So the idea is to use the Laplace approximation on deep neural networks. So if you heard, maybe you know already what it is, but just to have a very quick wash, what is in general the Laplace approximation? It comes from Laplace, so it's quite old but gold. And if you have distribution, a probability distribution like in green, and you want to approximate it with a Gaussian, well, what could you do? You can find the maximum and then put a bell on top. And how do you find how much the curvature of this bell should be? Well, this is given by the second derivative or the Hessian. So what you're doing, you do a Taylor expansion of your distribution or your log distribution. You take a second order expansion, and then you use what you can see. This becomes then in a form of a Gaussian, where the mean is given by your maximum, and then the variance is given by the inverse of the negative second derivative. And this is really like what you can see here. It's like you're just, in red, approximating this bell around the maximum. And this can be used in deep learning, and it was used for the first time in this context at the end of last century, but it was shown to be quite powerful in the last years. And how do you do that? How do you add the Laplace approximation to a deep net? Well, so normally when you have a deep neural network, they find the maximum a posteriori, which is the minimum of a loss function. That is divided into so on some data, you have this part that is the excess risk, and this is a regularizer, which in a Bayesian language are the likelihood and the prior. So when you can approximate the posterior distribution of the weights over the data, on the data, by a Gaussian through the Laplace approximation, where your sigma is going to be the Hessian of the loss, the Hessian in terms of the parameter of the loss of the data. Okay, and now we're basically done. We just have to put then the approximation over the output of the network. by linearizing the network. So basically, this is really just the next step forward from what I did before, from the GP setting in a linear case to a deep neural network. So approximately, I'm kind of having a GP where I now have an approximation over the posterior of the weights. What I have to compute is only this object here. So I have to know how to do efficiently a Hessian. Fortunately, there are actually quite efficient ways of doing that, because so what I want to stress out, and I think also what Philip stressed out, is that the computational overhead that you have to add to have this uncertainty is really just one computation more of this Hessian. And we can do it in a quite efficient way. Okay, and we did it. So we tried to use these tools of recent Bayesian deep learning also for the case of neural operators. Here I have an example that was taken actually exactly from the paper where the neural operators come out, and try to quantify the uncertainty there. So here on the left, you can see, so this is a PDE known as a Darcy flow, where the input was the parameter lambda and the output was the function u. What you can see is that this Laplace approximation manages to actually spot the errors of higher errors. So even if this two plots looks pretty similar, actually our uncertainty estimate can quite precisely spot the area of error in this plot. So here on the left, you can see the error. So for computing this, you need the actual solution and do the difference. For computing this, you don't need the actual solution. You're approximating and the uncertainty that you have. And another point that we wanted to make out of this is that also in cases where you have really little data available, which is actually quite a common or a usual setting, because if you think at very complex like weather models, producing this data can be quite expensive. You have to be aware if your approximation is very wrong. And this was the case. So here we use only 3 data points, so the solution is totally wrong, but our error estimation is actually of the right size. So you can really see that the model knows that he is wrong. Okay, now I'm going to do a step forward from what I was saying. And I said, okay, we looked at learning different types of operators. Now I go back to the case where we learn the operator G that maps F to U, okay? So, and we do this, as I said, as we did before, in a machine learning setting where you have some data and you want to approximate this operator, or you want to learn from this data the operator. And this actually opens the question, okay, but what did we do? Like, what does it mean in general to learn an operator? Because, as I said, this is a way more complex object than other things. And the thing is that you need, of course, to do assumptions on your operator. So, and here I put it a bit in the context of Bayesian approaches of learning operators between infinite dimensional function spaces, and the Bayesian approach is quite more sparse compared to other literature on not doing it in a probabilistic sense. But in both, like here I just mentioned 2 recent papers, they both do very strong assumptions on G. For this first case, they assume that it depends on a parameter and that they can sample from this parameter. In the second case, they actually assume that they can diagonalize this operator on a basis that they know, and then the problem just becomes to learn the eigenvalues. So you need, in some sense, to do a very strong assumption about this G. And in fact, our assumption was that this was an integral operator, so you were just learning the kernel of the integral operator. And then we recasted this problem in the language of inverse problems, because we wrote it in a way where then the problem was learning a function given this operator A. And this is what you do in classical inverse problem setting, where you have observations on U and G, and A is given in this slide. So what you want to do is you want to learn to invert somehow this operator in a stable way, such that for a new point U, then I have the new approximation G. Okay, and now I'm going to do even a stronger assumption. I'm going to assume that what I called before the green function has a is a univariate function. So it's this very specific form of being actually a function of one variable and being the difference between x and y. And what you can observe is that this function then becomes, this operator becomes a convolution operator. I'm sure you've heard already about convolution. We will see now quickly what it is. So if you have two functions, one is the original function f and one is called the filter g, convolving two functions, which is given by this formula here, how you can visualize this in your mind is you're taking the first function, then you flip the second function, because there is a minus here, so you flip it here. Sadly, you cannot see that it's been flipped because it's a bell, but actually you flip it, and then you move towards this line, and at every point you take the product and you integrate. So you take the area like under the product of these 2 points. So this is what it comes out, and the effect is the one of smoothing these strong peaks, right? Because here it becomes basically the same, because it becomes the same because we are at 1, but when you're at the border, it smooths out. And you have to think about this moving and integrating at every point. And so what I maybe want to stress out here, that this is a special case of before, because I'm here now, if I want to learn this convolution operator, I want to learn a specific type of PDEs. So it's a special case of the case that I treated before. But actually, it's also a starting point to think about a bigger question, which is, OK, what does it mean? What are the structure that needs to have an operator to be able to learn it? And in this case, I'm learning an operator that I know many things about this operator. In this case, for example, I know that it's diagonalized by the Fourier transform. So even though it's born as a special case, it actually is a starting point to think about a broader problem. And this is, in fact, what I worked on, and I'm still working on last year when I was in Genova. And the third point, actually, convolutions are at the core of many applications. So you can see convolutions in many different areas in science. For example, I mean, I have to start with PDEs because this is what I already said this, but repetita juvant. So if you have a differential operator and you have a fundamental solution of this operator, which is defined as when you give it to the differential operator, you are given with the impulse and an impulse response, so delta. Given this differential equation, you can call U a fundamental solution and compute the solution through the convolution with this fundamental solution. It's basically like the Green function. It's a bit more of a general theory. Like here you are not taking into account the boundary values, but it's the same idea. But note that if you have a fundamental solution, then you can compute solutions through a convolution. And there are important examples of differential equations that, or operators, sorry, that admit fundamental solutions, and they are operators that you probably have heard of, like Laplacian or the heat operator or the wave operator. Another example that is still connected to PDEs is that in differential equations, when you want to numerically compute the solution of a partial differential equation, one thing that you often do, or what you can do, or is known as the method of lines, is that you can discretize in space, your X space, and evaluate your U at this grid. So you instead of having this type of equation, you end up with ODE only in time, where you have discretized, you have now dealing with a vector. And to compute this derivative, what you do is also you discretize the second derivative, and you can do it with a matrix that is actually a discrete convolution operator. So I didn't talk much about what this convolution, I didn't talk at all what is the convolution in a discrete case, but since it's a linear operator, right, derivatives are also a linear operator, you can represent them with a matrix, and these matrices have a very peculiar structure. This is, for example, one of these. This is a Toeplitz matrix that is, it's just has the same value on the diagonals. And it's a discrete differentiation, but what is happening is it's convolving with the vector. So when you have this K, this matrix, and you give it a U, what is happening, you're convolving with the vector of increments here. So the second difference is you're sliding and you're computing a convolution. So what I want to say here is that, of course, there is the theory of solutions for fundamental solutions, but also when you deal with with discretizations in numerical methods, you're dealing with operators that involve discrete convolution. So also practically, these are used very often. Another example that I cannot mention are images. So I'm sure you've heard about convolutional neural networks and so, but what I want to say here is that if you have an image, it's a 2D object. What you do is you can work on an image, and when you convolve a kernel on that image, you have very different effects on the image. For example, here you choose a kernel that in this case is two-dimensional because we're two-dimensional. Then it blurs out the borders. You can sharpen the borders, or you can only outline the pixels that have the major differences with its neighbors. And what is happening here, literally, when I wrote this code, was convolving this kernel in the image. And as I did in one dimension that I slide it, you just take the kernel and you slide it along the image. OK, the last example that is comes really from the basics of probability theory, but I like it when it's a very simple example but gives you kind of an intuition, is I'm sure when you studied probability theory, you studied that the probability of the sum of two independent random variables is given by the convolution of their individual distributions. And this is what is written here, right? So you have this is really the formula, but just discrete with a sum. So imagine that you have two dices. Actually, I took this example by a YouTube channel known like 3 Blue, 1 Brown. I don't know if you know it. If you know, look it up because it's great. So imagine that you have two dices with, and you want to know, these are the two random variables x and y's, and you want to know what is the probability of the sum. So what you can think to do is like, here you just put all the numbers on two lines, and you flip the second one. And the probability of having a 2 is just given by this option, right? That the first dice is a 1 and that the second dice is a 1, OK? What is the probability of having a 3? Well, I'm just taking the second dice and sliding in one position. And it's either the first one is a 1, the second one is a 2, or vice versa. And this happens all the time. If I want a 4, I will slide another one down. And now if you imagine that you don't have a uniform distribution, but you have actually some weights on the numbers of the dices, what you do is you're going to take the product of every like P1 multiplied by the probability of having a 3 in the second dice, and you sum them up. And this you're going to do all the way around. So what you're taking the second line, and you're sliding it up. So you're actually convolving these two distributions, right? And in general, when you have this case where you have a vector and you slide it and you just make it roll, this is when a convolution is a good way of imagining how a convolution happens. And maybe in a practical case, you could think that you know the probability of z, you know the probability of x, but you don't know what the probability of y is. And this would be exactly the case that I said. What you were doing there implicitly is you're learning a convolution. OK, now I think I convinced you that there are so many convolutions in the world. So it's an operation that actually shows up in a lot of seemingly unrelated areas. And now where a bit of the nasty part comes more is that we wanted to actually investigate theoretically how to learn it. And we do it in the language of the RKHS or Gaussian processes. So when we look for to learn through data in an reproducing kernel Hilbert space. And actually, I want to point out the main 2 points that I want to do of this last 10 minutes that I'm going to talk about how to learn a convolution operator. The first one is that you can talk about objects that might seem very complex, like operator-valued kernels or GPs on operator spaces, actually in a very tractable way, because you don't have to care about it anymore, because you know how to do that, because you know that the structure of this operator is cool. And the second one is that when you want to study like convergence rates of your approximated operator, what you normally do is that you have some source conditions on the true solution. And these are normally very abstract, and that's quite difficult to verify. But this is not the case for convolution, where we get with some conditions that we can quite easily interpret what they mean. OK, this is a bit of a step back. So in a classical overview of in a classical scalar case, where you have data x and y in a machine learning setting, and you want to learn a function. So imagine we are in a really scalar case where f maps between x and y, that x are d, and R is just a scalar space. So it's a very classical space. So what you do normally is like you fix a parameter space, and you consider feature maps. Now here I'm doing the feature map construction for what will be clear before. So you look for functions that are of this form. So you end up, what you want to do is like, this is equivalent to look for parameters in H. And these functions actually generate, by the varying of W in the parameter space, a reproducing kernel here of the space with a kernel that is given for every point x and x prime by the scalar product of the features. I hope you're familiar with this, but this is quite a standard setting. And you can, when in the GP language, when you're going to find the mean of your approximation, it's going to actually be the same you find when you do kernel regression in a reproducing kernel Hilbert space. Okay, and now I do a step more of abstraction. Now I assume that these spaces x and y are not anymore Rd and R, but they are general spaces. Think of them as function spaces. That's why what I'm learning here now, f, is an operator between function spaces. Okay, and what do I need to change in this classical setting is that my feature map has to go into the right space, right? So it's going to go into the space of operators from H to Y, and it's going to be defined by, for every W and X, I will have not anymore the scalar, like the inner product between W and phi of X, but it's going to be phi of X acting on W. And then with this, my kernel will be just this object here. So, and notice that this goes to the right space, right? This object, phi x of W, is in Y, which is in general function space, whereas here it was a scalar. And this sorry, this is an error here. I forgot to change this. This is very wrong. This should be the space of operators from Y to Y. So this should also be in red. And notice that here you are in an isometry. You can move from W to F, like preserving the inner product. Okay, and the only thing I want to stress out here is that for convolutions, I can tell you what H, phi, and the kernel are, because because of the structure of this operator. So here, this f of xi is just the convolution between xi and W. So as the scalar space, I will choose a reproducing kernel here, say with a scalar kernel, k. And the feature map is going to be just given by the convolution from x and y. And my kernel is also going to be a convolution operator, where actually there is a direct connection between the kernel k in the scalar space and actually the convolution kernel. Again, I'm sorry, here it should be, it goes to a space of operators. That was actually the main point, and it's wrong here. But it's like, it should go to a space of operators from y to y. Last observation is that doing this in frequency domain becomes way easier, because a convolution operator in frequency domain, it's just a scalar, it's a multiplier operator. So convolving with this object is just going to be multiplying with this object. So we can actually compute the solution of a GP mean regression or of a kernel ridge regression analytically with computations and write down what it is in terms of the frequencies of the observations. Okay, this was a lot of math, so let's look maybe at an example to visualize. Here we have some input functions, where I just took some trigonometric functions and sinusoids and cosines, and the observed function. So here are my inputs and my outputs. And there is a function acting between these two plots that you can't see, that is the function you want, the kernel of the convolution you're looking for. And well, let's find it. The function I'm talking about is the real function is the one in dotted lines. And here you can see the approximation of this function under two different kernels chosen, one that gives way more smooth samples or functions, and one is more smooth. And here is just to visualize a bit this changing the kernel here for two different values of nu. So we choose a Matern kernel with varying parameter nu, and seeing how this actually affects the approximation. You can see here what is known as the Gibbs, like an effect that you're learning a discontinuous function in 0. So you're going to see the effect on the border. And of course, you can do this also with uncertainty. So you can add uncertainty to your solution. But keep in mind and remind that now here I'm showing you a function, but what you're approximating is actually an operator. So the uncertainty that you have on this function is actually an uncertainty on your operator because of the way of the framework that we said before, right? It's really easy to move from one space to another. So I can talk about objects like uncertainty on operators or operator value GPs in a doable and not in a tractable way. OK, this is actually the last slides, and the main point that I want to make about it is, as I said, that usually convergence rates are, in general, they rely on source conditions, and they're, in general, very difficult to formulate and to be verifiable. But in case of convolutions, I can see them here. You can actually see that what is normally in a very abstract form is tractable. So you can see that what will affect the convergence of the algorithm depends on how the speed of the Fourier coefficients or the Fourier transform of your true function compared to the ones of your kernel that you've chosen, but also of the distribution on your inputs. OK, and I know this was probably quite unusual talk because, I mean, I started from PDEs, and then I talked about Gaussian processes, and then deep neural networks, and Laplace, and then convolution operators. So I know it was a lot of things altogether, but I hope that you kind of managed to find the fil rouge against all the story and how it came together. So maybe here a summary to sum it up a bit. So we started by asking what is to solve a PDE and defining solution operators of partial differential equations, and then using probabilistic methods that use GPs to learn the kernel of these integral operators. And then we looked at more complex solution operators that are nonlinear in the inputs, and so we have to use models that use deep neural networks to approximate the solution. And to add uncertainty also to these models, we use the Laplace approximation. And then this was then a starting point to think about what it means to learn an operator in a probabilistic way, in particular convolution operators. Thank you. And as I said, there is still more to say and more things to look more deeply. I'm happy to receive questions. And I know I took maybe a bit more, so if you want then to come for questions, I'm very happy to chat about it.